Processing course. In the first module, we will take a look at the principal objectives of modeling and go to the finer details of data cleaning in the subsequent modules. The white rabbit put on his spectacles. "Where shall I begin, please, Your Majesty?" he asked. "Begin at the beginning," the king said gravely, "and go on till you come to the end. Then stop." Lewis Carroll was not only a famous writer but also a mathematician and a logician, and it's no wonder that he thought like a computer scientist of today. In fact, this is how algorithms begin with a start button, then goes on to read data, calculate things, read out the results, and eventually, when everything seems done and nothing is left, then finally stop. So for our data cleaning and pre-processing course, let's begin with the first step of identifying the task. Whenever we are given a problem to solve in any field of learning or in any aspect of life, we first need to identify our task, that is, what we need to do. Knowing the task properly, and of course having a prior knowledge of how to achieve that task, would greatly help to plan the next steps accordingly and link your goals to the materials at hand and the tools at your disposal. For a data scientist, a machine learning task can be categorized into one of these two broad categories. The first is supervised learning, where there is sufficient information in the data set that actually guides the algorithm to correct itself when it learns the wrong way and coerces results to keep on the right track. This means the way the computer learns is supervised by some information in the data set itself, and this information is typically found in the last column of a data and is called a class or target variable. Of course, some data sets may have the target variable in the beginning or somewhere else, maybe in the middle, but it's customary to put the output information in the last column. Typical examples of supervised learning are classification and prediction. Both of these tasks are almost the same, except that the nature of the target variable, which is discrete in case of classification and continuous in case of prediction. Now, the other category of machine learning tasks may be called unsupervised learning. In this kind of learning, there is no concept of right or wrong, and whatever you do with the data or whatever relationships you can find in the data will add value for people and give meaning to the numerics in some way. Of course, unsupervised learning is more difficult because you need to figure out what are the kind of things that people exactly need from the data. Just visualizations and correlations, or similarity of data points, interdependence and redundancy, or something else. And you need to write a code or call a suitable functions that does just that kind of things to the best possible extent. A typical example of unsupervised learning is clustering. With that said, it's worthwhile to note that there are machine learning tasks that fall somewhere in between these two distinct categories. They are called semi-supervised learning algorithms. Such tasks use partial information on the class or some target that is to be achieved, maybe for a small part of the data or with some amount of uncertainty or imprecision in the output information. Now let's take a one step closer look at these three most common tasks. What would be provided, what do we need to do, and finally what are the deliverables at the completion of a task. Now, classification is in fact the task of building algorithms that can learn how to distinguish between objects of different classes. So if you have a set of pictures, maybe profile pictures of different people, you can try to train an algorithm which will differentiate between males and females from the nose, eyes, or different aspects of the pictures themselves. Of course, the gender of the persons should be known, and this bit of information actually supervises the algorithm, but the training would be such that the algorithm should be able to classify males from females without having to look at the class or gender information. So learning usually starts by generalizing a given set of objects, looking at what features and what are the range of their values that are common to the same class but varies across different classes. This generalized knowledge takes the form of a model and is used to classify new objects whose class information is not known. Sometimes we test or evaluate the performance of a model by keeping aside a part of the data with known classes and see if the trained classifier is actually able to distinguish the classes properly. The percentage of objects it correctly classifies is most commonly attributed to the accuracy of the model. Now we will come to this training, testing and evaluation of models and see how to prepare our data set accordingly in one of the later sessions of this course. But just to conclude our preliminary understanding of what classification is, we just note a few examples or applications of classification, namely face recognition, fault detection or medical diagnosis. In some cases there could be just two classes, what we call a binary class problem, whereas in other applications there could be 3, 7 or even more classes, often called a multi-classification problem. The next most important task and a model built around it is prediction. Prediction, also known as regression, involves estimating some particular attribute of new objects, for example age of a person or chances of winning a match, based on a training set of data with given features that take up different values under diverse conditions. The task of the predictor is to achieve a level of training so that it will be able to predict that particular required attribute from other features of the data. It's almost the same as classification, only here we have a continuous spectrum of values of the target attribute rather than a few distinct classes. Examples include predicting the strength of an alloy from its composition and heat treatment, estimating the chances of rain from current weather conditions, or speculating the lifetime value of a customer for some relevant business opportunity. There are many models that can perform both classification and prediction, though with some changed settings, but of course there are models dedicated to do just prediction and that don't work on classification tasks. So we need to be careful while choosing our model for the different tasks, and sometimes even the data cleaning requirements could be different depending on the task to be accomplished. It is also good to know that some models are static models which don't change over time, whereas there could be also models that predict attributes differently at different times, called time series models. Share price variation or weather models basically belong to this latter variety. While a static model is created once for all and uses the entire data to make predictions that are valid anytime, time series models make different predictions for different time settings depending on a small part of the data over a definite period of elapsed time slot. And finally, clustering, one of the most popular unsupervised learning tasks, refers to grouping objects that are similar in many respects. When plotted on an XY Euclidean axis, similar points seem to cluster together, and it is the task of a clustering algorithm to find out which objects best fit into which cluster. A pre-task could be to determine the most suitable or optimal number of clusters. Sometimes clustering is used to stratify a large group of objects or choose one or a few objects from each cluster that would represent a standard object of that cluster or group, essentially exhibiting the same kind of behavior and capable of or replacing any object from that group. Examples include constructing persona for ad targeting or categorizing similar products or web pages. So that was a bird's eye view of the kind of tasks that we need to do in machine learning. In the next module, we'll take a quick trip on how one of these tasks are actually done with a small data set.